Okay. So it turns out refraction, as well as reflection, we'll find out, has a chance to occur when light goes from one medium to the next. So let's say we have light coming from the air and about to go into water. So when it meets the surface between the two mediums here, so two things can happen. We might get a reflected ray. And so in this case, if we call this angle right here the incident angle, what would be true about the angle of reflection? It'd be the same. But some of the light is also going to get transmitted into the next medium and not be reflected. And this is where we talk about refraction. So it turns out we got to talk about what's called an index of refraction first. So it turns out, what's the speed of light? 3.0 times 10 to the 8th meters per second. Well, it turns out that's not an adequate definition or assignment of the speed of light in this chapter. So it turns out that is the speed of light in a vacuum. And it's almost nearly exactly the same number in air. But it's not the same in water. It's not the same as it travels through glass or any other material. It turns out it's going to go slower in any other material. So when we say the speed of light, the question really should be in what medium? So are we talking about vacuum or air, or are we talking about something else? So, and it turns out the index of refraction is characteristic to the material. It takes the speed of light in a vacuum, 3 times 10 to the 8th, and then divides it by the velocity in that actual medium. And so in this case, because the speed of light in a vacuum is always bigger, these indexes of refraction are always larger than 1. And so in this case, if I told you I had an index of refraction of 2, what does that mean about the velocity in that medium compared to the velocity of the speed of light in a vacuum? It's half. You know, if you rearrange this here a little bit, you could say that v would equal c over 2. So it'd be the speed of light over 2. So if your index of refraction is 2, it's just only going to have half the velocity as it would be in a vacuum. If it's 3, it'd be with 1/3. If it's 1.5, it's 50% slower, so on and so forth. So if you recall light, the speed of light, is related to its wavelength and frequency through this equation. This would be in a vacuum. Well, it turns out, you know, if we're not in a vacuum, then I guess we should use the letter V instead. And it turns out the frequency does not change as you go from one medium to the next. The frequency does not change at all. Whatever frequency it had from one medium, it's the same exact frequency in the next. So, but even though the frequency hasn't changed, if the velocity's changed, something has to change, and so it must be the wavelength. And so the wavelength's going to change. And so it turns out like the color of the light's not going to change or anything like that. You know, as we usually associate a color with a particular wavelength, we could have just as well associated that color with a frequency as well. And the frequency is not changing. And so the color, if it's in the visible region anyway, so that light's not changing. But the wavelength and the velocity are both changing. If the velocity was twice as slow, or half as big, if you will, then that means the wavelength would be half as big in that medium as well. But again, the frequency wouldn't change. Everybody cool with that?